We know ionic compounds and molecular compounds are very different because ions are held together by positive and negative, are made of positive and negative ions that attract each other strongly, so they can grow into these giant crystals, whereas molecules are discrete units held together by bonds between atoms. Well, what we're looking at now is what actually holds the molecules together. And there's several different forces that are responsible for that, and these are called intermolecular forces of attractions. Inter, of course, means between, so this is not intra, this is inter. So intramolecular forces are the chemical bonds, that single, double, triple bonds that hold the atoms together. But intermolecular forces, these are what holds molecules together. So when you look at a grain of sugar, that's actually thousands of molecules of sugar all stuck together. And the reason they stick to each other is because of the partial charges, right? So whether or not they're polar kind of influences these, but there's other intermolecular forces, and we'll take a look at those. So it is actually the attraction for these opposite partial charges that results in these compounds sticking together. Now, intermolecular forces of attraction are much, much weaker than chemical bonds, so it is not nearly as strong as ionic, covalent, and metallic bonds, which we've not talked about. But metallic bonds are also a fairly strong chemical bond. Intermolecular forces of attraction are sort of like the equivalent of holding magnets next to each other. They attract each other, but you can still pull them apart. It's not as strong as the attraction that holds, say, the ions in a crystal together. Now, we're going to look at what the different intermolecular forces of attraction are and what properties they cause. Basically, the stronger the attractions between things, the harder it is to get the atoms or molecules apart, and so the state of matter will depend on the intermolecular forces of attraction. So stronger forces means it's more likely to be solid. Weaker forces means it can be liquid or gas. Temperature also affects that, right? If we give the particles more kinetic energy, they can overcome their attractive forces and spread apart. Intermolecular forces of attraction also influence how easily something evaporates. If it's got strong forces, it's going to take a lot of energy to get them apart, and so they'll want to stick together. They'll have fairly high boiling points, whereas weaker forces allows them to be easily separated, so they won't stick together as well. So weaker forces of attraction, lower boiling points. Which is what this one is about, boiling points and melting points. So evaporation is technically not the same as boiling, right? Boiling occurs throughout a liquid when the internal pressure is greater than or equal to the external pressure, whereas evaporation just occurs on the surface. But the net result is the same. We have particles entering the gaseous state. Now, here are a few substances: hydrogen, oxygen, chlorine, and methane. These are all very nonpolar substances, either because they are the same atom, so there's no difference in electronegativity, or because the molecule is symmetric, and so no side of the atom pulls the electrons closer to it. And you'll see their boiling points are all very low. Minus 253 to minus 164, 183, minus 34. Then we get into these polar things. NH3 is slightly polar, because it's asymmetric with its trigonal pyramidal geometry, and it's got a fairly low boiling point. It's close to chlorine. HF is actually going to be a very polar molecule. It's got a relatively high boiling point, considering it is a light molecule. And then there's water, which has a great a high boiling point. It's a very polar molecule as well. So you can see different types of substances, polar versus nonpolar, are going to have very different boiling points. Now, the fourth property that we talk about is miscibility, and this is whether or not two substances mix together. You've probably heard the expression like dissolves like. You've also probably tried to wash oil or grease off your hands with water, and it does not work. Water is a very polar molecule. It will attract other polar molecules to the exclusion of nonpolar molecules. The water molecules stick to each other, but they don't stick to the nonpolar oils, and so they don't mix together. Nonpolar molecules will stick with nonpolar molecules. The forces of attraction are relatively weak, but they'll do it. So the way soap works is it actually has a polar side and a nonpolar side, so it can mix with both, and so then you can dissolve your nonpolar substance into your polar substance. Now, it is worth noting that ionic compounds usually dissolve very well in water. Water's polar. Ionic compounds have positive and negative charges, so there is an attraction between those things. Now, I said there are a variety of different intermolecular forces of attraction. Let's take a look at them. The strongest one is hydrogen bonding, which is not a bond. It is between molecules, not within a molecule. So don't get confused by that. It is the strongest intermolecular force of attraction, and it can only occur when we have hydrogen bonded with oxygen, fluorine, or nitrogen. Dipole-dipole interactions. A dipole, remember, that's our positive and negative on a polar molecule. So these act like little magnets and stick to each other. So this is basically the same as hydrogen bonding, but since the electronegativity difference will be less, it's not quite as strong as a hydrogen bond. And then we have dipole-induced dipole interactions. This is when we have a polar molecule that induces a pole in another molecule. It's temporary, they don't last very long, but it can attract. And then we have London forces, or London dispersion forces, which basically arise due to the random motions of electrons. So we'll look at each one of these in a little more detail. So we'll start with hydrogen bonding. Like I said, we have to have things that are very, very polar, which is why this only occurs between fluorine and hydrogen, oxygen and hydrogen, and nitrogen and hydrogen. Those are our three most electronegative atoms, so they are the only ones that can form hydrogen bonding. So the very strong electronegativity of fluorine, oxygen, or nitrogen attracts the electrons off of that hydrogen atom. And remember, that hydrogen atom only has one electron, so if it's mostly attracted to the other atom, that leaves the hydrogen exposed with its proton, and then the other side has an extra electron. So this is a very, very polar molecule, very, very polar bond that can occur with hydrogen bonding. So water will hydrogen bond. DNA, the two strands between the base pairs, those are held together with hydrogen bonds. And then proteins, they fold over on themselves and get a shape, and that's because hydrogen bonding within the same molecule pulls that chain of amino acids into the shape that makes it a protein. So remember, this is not within, it's not, hydrogen bonding does not occur between fluorine and hydrogen. Hydrogen bonding can occur between two atoms that have, or two different molecules that have the fluorine hydrogen bond, or the oxygen hydrogen bond, or the nitrogen hydrogen bond. So hydrogen bonding in water is why water, even though it's a tiny little molecule, has a very high melting and boiling point. It melts at 0 degrees and boils at 100 degrees. And it also is the reason why the solid state is less dense than the liquid state. Usually we think of as particles cool down and turn into a solid, they come closer together. But in water, the hydrogen molecules are attracted, or the hydrogen side of the molecule is very attracted to the oxygen side, and they actually align themselves in a crystal structure that's sort of hexagonal in shape, and there's extra space between the molecules. It's empty extra space, there's nothing there. The atoms or molecules are just arranging themselves in a nice crystal structure. And so when we have two molecules, say water's H2O, it's bent, right? And we have a very strong negative partial over here and a strong partial positive over here. And then we have NH3, which has its 3 hydrogen atoms on it. And this will be fairly strong negative, partial negative over here, partial positive over here. These two molecules will align themselves so that the positive here attracts the negative there. So we might end up with oxygen, hydrogen, hydrogen, right? A little Mickey Mouse, and then nitrogen is going to stick over here, and it's got its 3 little hydrogen buddies here. So this attraction between these two molecules is what we refer to as the hydrogen bond, and it arises because of this very strong partial positive and this pretty strong partial negative due to the electronegativity difference between hydrogen and oxygen. Now, dipole-dipole interaction is basically the same thing, only it's without the hydrogen bond. So it occurs when the positive and negative partial charges of two polar molecules attract. Hydrogen bonding is stronger, so we do distinguish the two. If both molecules have this, then we have hydrogen bonding. If one or neither of the molecules has the FH-OH or NH bond, but they're still polar, then they have dipole-dipole. And so HBr with itself and with water. So bromine is not nitrogen, oxygen, or fluorine, so it can't produce the hydrogen bonding, but it does still have a dipole this direction. So we have our positive here, we have our negative here. Water also is polar. It's got its oxygen, hydrogen, hydrogen, partial positive here, partial negative here, but because it's not in OH to OH, or an OH to FH, or an OH to NH, or one of those three combinations, this is still just going to be a dipole-dipole interaction. So the interaction between this, we'll get our HBr stuck over here with its partial positive. So this attraction, that's the dipole-dipole interaction, and it's weaker than a hydrogen bond. HBr will also form the same dipole-dipole interaction with itself. Dipole-induced dipole occurs when we have a polar molecule and a non-polar molecule, and basically what happens is we get the polar molecule to temporarily change the charge distribution on the non-polar molecule. So if you think of, say, water and nitrogen, nitrogen actually will dissolve in water, and we don't think of those two things as being miscible because they're not two like things. But nitrogen is slightly soluble in water, and that's because we've got water, which is very, very polar. So we've got this positive, and we've got, or sorry, that's negative, and we've got this positive, and then we have nitrogen, which is triple bonded to itself. And then it's got those lone pairs of electrons on the end. It's a linear molecule. Well, when this nitrogen atom gets close to, say, this end of water, the negatives are going to just kind of slightly push these electrons away, and so we end up with a greater electron density over on this side. And so now this is slightly negative, this is slightly positive, and there's a weak attraction there. This is in normal space, we would not consider it as polar, but because it is being manipulated by this other polar molecule, we get this induced dipole where this is slightly negative over here, or slightly positive over here, and this is slightly negative over here. So you can push electrons around this cloud of these two atoms in the molecule and get a dipole-induced dipole interaction. Now this is temporary and weak. So polar molecules are always polar. The electrons in here are going to tend to redistribute themselves back symmetrically, and so this is going to be a temporary thing. It's going to form, unform, form, unform, which is why nitrogen is only slightly soluble in water, not really soluble in water. Then we have the London forces, and London forces occurs naturally in everything, all molecules and noble gases, and that's because electrons are in constant random motion. And that means occasionally electrons are going to end up piled up next to each other and farther from each other. And so you get very temporary fleeting dipoles. And so that means that we're going to have molecules that are temporarily attracted to each other. However, when you have lots of atoms in your molecule, you have lots more electrons, and so you have a lot more abilities for these to happen. So hydrogen, which is our simplest molecule, two hydrogen atoms bonded together, has a boiling point of -253. There are not a lot of London forces in hydrogen because there's not a lot of electrons. But you look at I2, right, big old halogen, it's got lots and lots and lots of electrons. Those electrons are constantly arranging and rearranging themselves, and its boiling point is actually 184. Iodine is a solid at room temperature. And then if we continue with this, we have more London forces with bigger molecules, higher melting points, higher boiling points. And then if we also have any other intermolecular forces of attraction, that's also going to greatly increase the melting and boiling points. So you can use intermolecular forces of attraction to predict which substances will have higher or lower melting and boiling points. If they're similar in size, the one with more intermolecular forces of attraction will have the higher melting boiling point. If they have similar intermolecular forces of attraction, the larger one will have more London forces, so it will have the greater melting and boiling points. So neon, which is a noble gas but has an atomic mass of around 18, and H2O, which has a similar atomic mass, around 18 atomic mass units. Water has very high melting and boiling points because it's polar, hydrogen bonds with itself, and neon with very low melting and boiling points because it's a very small atom, and the only thing that holds it together are London forces, and they are very weak. And then neon and argon are going to have different melting and boiling points because argon being the heavier atom, it's got more electrons, and so it will have a slightly higher boiling point than neon. There's a little bit more London forces going on there.